Morning, everybody. They told me I could just enter, right? Well, first of all, congratulazioni per l'inaugurazione dell'Unimore AI Center. Amazing news. I'm very happy to be here today. I didn't know how to structure this because I tried to keep it a bit high level. I didn't know who would be in the crowd. Right, so I took all the equations out, but if you really want the equations, feel free to come to me afterwards. They can give you notes, right? So the idea today was in the 24 minutes I have left, give you a bit of a highlight on what we are doing, not only in ELLIOT, but in general, and hopefully persuade you that this is an important thing that we should be looking at. The title is Document Understanding, but in reality, what is a document for me is a much more wide thing, because if you think about it, you are surrounded by documents in your everyday life, right? So if you think about what would it take for an artificial intelligent agent to solve this task, you realize very fast that unless you can actually understand all this hidden information that we have left in writing in the world around us, computers are just incapable of working with us in urban environments, right? So that's more or less what is driving our research. And it's true that all the data sets that we have been using in computer vision for the last 70 years, and the big ones that we have been using in the last 15 years, they have loads of text inside them, and computer vision has been illiterate for the past 70 years, right? It's only very, very lately that we have been looking into how much all these large models actually understand text which is around us. And when I speak about written communication, I don't just mean text, right? Because we have loads of ways to communicate in writing information for other people, right? Be it symbols and color codes and diagrams and maps, and they are scattered all around, all the way to touch interfaces, right? Haptic stuff that you can, by the way, also interpret through vision in most of the cases. So understanding all these kind of hidden messages that we have left in the world around us, it's kind of important, and we cannot expect that computers would be able to collaborate with us if they're not able to do that. And know that although we have not explicitly taught computers how to read, if your models become large enough, they automatically understand how to exploit this information on their own. This is like 15 years old, right? It's some research from Google on classification of business streets, businesses on street view. And they realized very early that they were doing extremely well on images that basically were just window, right? And they were very, very curious about why this happened, and they started feeding the classifier with images like this, and the classifier was doing pretty well, right? So it had learned basically how to exploit this information without explicitly being taught how to read. And nowadays, of course, you see that every time more, right? So this is that clip is very sensitive to text and images, right? So if you just start adding text and images, you can make clip do strange things. And it's even more than that, because in reality, all these models, they start learning to place in the same neuron a number of different representations of the same semantics, right? So it doesn't matter really if you're talking about an image of a spider or the word of a spider or a drawing of a spider. It's the same neuron that activates. And you can look into that a little bit further. And these are, random neurons from the penultimate layer of a trained clip model. And what you see there at the top is kind of this deep dream representation of what maximally activates this kind of neurons. And what you see at the bottom is patches from the training set to which this neuron maximally responds. If you look at all these neurons of trained neurons of these models, you'll see that the vast majority of them actually respond to text, right? And it's interesting to understand what kind of text. The titles there are mine, right? It's just my interpretation of what these things are doing. But you see, you have neurons that specialize on Japanese kind of sounding stuff, right? And other that specialize on buying. Another, I call this one a pessimistic one because it responds to things like, failure, later, this kind of very, very bad things is my fault. It's very strange how they capture the semantic things. And there are other neurons that actually capture the actual transcript. Yeah. So there are neurons that respond to specific letters, no matter which word they come in. So it's very strange to understand what these models learn about reading, about understanding this kind of written communication without us teaching them anything. So that's prehistory, right? Because that's something that we did many years ago. But back in the time, before GPT was a thing, we thought that we should maybe try to see how models respond to questions that require the models to actually read the text in the images before they manage to give an answer. We created this data set. And what we found out was that the best way to train a model to do well in this kind of settings is to take the model and pre-train it on real paper documents, right? So you take loads of paper documents, classic documents, and you just make the model transcribe them. And this way the model basically learns how to read, and then they do much better, of course, in this kind of task. And then at the same time, more or less, we came up with this idea of why don't we bring this visual question answering scheme to real documents, right? And we invented this document we create task that very fast became pretty important, right? So May 2020 is more or less the time when GPT became part of our vocabulary, right? So we did this before foundation models were a thing, but then eventually all the foundation models started evaluating this kind of benchmarks, right? And they are still, I don't know why, but they're still using it. So that felt nice. I finally felt that I made an important contribution to science. But then you look at the performance of this thing, and then I started feeling bad because in the beginning, it's true that this created a whole shift of paradigm of how we do things in document understanding and the documents, which is cool. But then all this, we went through multimodal transformers and then eventually foundation models, and these things nowadays basically perform equally well as human performance, right? Or very close. And I felt bad because that is the wrong message, right? The message that we give here is that documents are easy, and that is definitely not the case, right? So I'm trying to fix it, right? And I'll try to explain you why this is not the case and why we're still quite a long way from having systems that can actually understand what is data communication. So in most of the cases, what people do is basically take a document, pass it through an OCR, and try to answer questions. And that is basically working with this, which is not really any close to what a document is, right? So if you think about a document, this has structure. This is not just text. This is text which is structured in a particular way for a reason, right? And you have to understand the structure. And understanding the structure is not just understanding the layout as a structure itself, how spatially things are related, but also understanding the logic, what they represent and how they relate to each other, right? And then, of course, when we speak about documents, we speak about images, and these images are thousands by thousands of pixels. Therefore, native resolution is important for us, right? We cannot just resize things and expect that reading will still be possible. And of course, we're speaking about documents, and documents is not a single image, there are multiple images, and it's not videos. One image from the next is very, very different. And nowadays, we're actually speaking about collections of multi-page documents, right? So every time that you want to do things like new science, and you need to tap on knowledge that is already there, or fact-checking, and you need to look at all the information that you have, or just businesses, right? All the documents you have in a business. We're talking about dealing with masses of documentation that somehow we have to go through. And that is not, that it doesn't fit in memory. It's as easy as that, right? So we have to come up with new ways of doing that. Nowadays, agentic is so I think it's a big thing. So when somebody speaks about documents, people think about this kind of thing, right? But when we speak about documents, we should start thinking about all different types of documents. And you see that there are loads of visual languages there that are being used, and depends on what you want to do. The visual language of a musical score is very different from the visual language of an infographic, right? So in the way a line is used in a musical score is very different from the way a line is used in an engineering, right? So unless you understand really what the domain is and why things are like this, you haven't even started, right? And everything is focused on classic administrative documents, and that is just the tip of the iceberg, right? And I'm not going to speak about when people get crazy and children start making little drawings and you just put a note in a napkin, the rest of it. These are documents, right? These are documents, and you invent languages as you go by, right? So this is really where the challenge is, right? And for us, the way forward basically means a couple of things, right? One thing is there is loads of domains that we haven't even touched, right? So we put a new data set out that came out a couple of weeks ago. It was trending in Hugging Face for a while, and I don't know it has already how many. They will tell me 8,000 downloads or something like this. And the only thing we did really was focus on some domains which are different, right? And let me explain you what I mean with this, right? In this data set, the top foundation models that we have right now, Geminis and GPTs, they're doing close to 40%. Right?
Well.
The kind of questions that we want to be able to answer are things like this, right? So look at the map, right?
Well.
The map means navigation, means to be able to spatially reason about the world, right? So this is a simple question. I'm standing at number 30. I want to go north. What's the last thing I'm gonna see? It's all about understanding how a map is laid out. But if you think about it, you need to first of all understand where north is, right? Then you have to find where this number 30 is in the map. Then you have to draw a line that is aligned to where north is supposed to be. Then you have to find where the last thing
to do well.
That doesn't work.
To do well.
Sorry, technical problem.
To do well.
You have to find where the last thing in this map is, right? And pick the number there. And then you have to go to the legend and then find this number in the legend and read it out loud. Now, that's a complex multi-hop operation that requires that you are spatially aware of this map thing of yours, right? It's a document, but it's a very, very different visual language, right? And of course,
to do well.
All state-of-the-art models are completely off when they try to do it, right? And enter into infinite loops when they try to explain this. Or this kind of thing. That's a comic, right? And you want to understand the story if you want to answer this kind of question, right? So we're talking about somebody that was murdered, and what is the last thing he did, right? So you have to first find visually or textually, right, when this event happened, and then you have to go back in time, right, and understand which places this person has gone through, right? So this is the last place. This is where he was murdered. This is the last place he visited before he was murdered, right? So it's a complex situation there, right? So we have loads of things like this. And we classified all these questions in a number of different types of reasoning tasks that need to be done. Of course, in the different domains that we are tackling, these tasks are represented in different ways. And I think that there is a lot of things to be done there. Currently, the models these are the error rates of the models, and you see that they make mistakes all over the place, especially when it comes to spatial navigation, to multi-hop reasoning, to layout analysis. That's also pretty important. And you can do better in some certain ways. So if you just focus on one of these domains, you can pick comics, for example, and try to come up with interesting tasks which are very comic specific. Like, for example, that's some work we did last year where we took loads of panels of comics and we started asking questions. What is the panel that follows? What is the right text for this panel in the middle? And that forces the model to understand more or less this visual language of comics. And that's good for comics. But we're not there yet, because what are the kind of tasks that we can put to the systems to become good all over the place, right? To become good on documents they have never seen before, the visual language that they just invented, right? Humans are good on this. So what are the ways to have honestly no clue about what are the best tasks? And then the second thing leveling up is document collection, right? So this first kind of approach is about understanding more different domains and different things that happen in different visual domains. But there's another kind of question that has to do with scale in a different setting, which is loads of documents that we have to search for answers, right? So that's a paper. This is the last slide. I edited 5 minutes before I entered the talk because the archive link just came out. That's a collaboration that we had with Snowflake, Hugging Face, Oxford, a number of very interesting people. And what we looked there is on questions asked on big collections of documents, right? We have documents from 2 pages to 800 pages, and we have collections of documents, and systems have to go in there and figure out how to combine information from different places to answer different things. And that's the kind of thing that we put together because we wanted really to test for the first time all this agentic thing that people are putting together in a real setting. And I will not, it's impossible for me to show you examples there because I would have to show you an 800-page document there into the slide, right? But the whole point there is that you have to go and combine information from a number of different places before we can even have a chance of answering this kind of questions. And there's a lot of information there. Don't worry. Let me say a couple of things. One thing is that we tested non-agentic systems, right? So just a very simple static retrieval and then try to answer thing. Then we tested a number of agentic systems. We gave different types of tools to different types of models, and we tried to see what comes out there. And then we tried humans, both humans where we gave them as an oracle, the right pages that they should extract the information from, and also humans that basically they got the same interface, search interface, like our agents. So they could search basically in the same way, right? So that we can compare similarly. And on one hand, we tested accuracy, which is basically how well we're doing the task. But on the other hand, we basically tested, let's say, efficiency. This paper metric is a way to measure how much effort you have put in the task. So the lower the number is, the better, the more fast you are able to complete the task, right? And you'll see that you do have some models that kind of get more or less at the same performance like humans, but at 3 times the effort, right? So there is, depends how you look at it. There's lots of ways that you can improve this kind of things. And in the agentic thing, there's loads of different things we did, including simple text-based search. We tried programmatically, this kind of agents that basically treat the whole collection as a variable, and they can programmatically try to attack this kind of thing, create tools basically themselves to extract information there. We tried the command line based tools for different agents, and these are different things that we see in the table. You can have a look at it in the paper, right? I'm not going to go into details, but the main summary here is there is, although some of the models are performing well, efficiency for these models is still pretty bad, and there is a long way to go to actually deal with this. This is more or less a comparison of the types of errors that the models do, and you see that they struggle a lot in the multi-hop thing. They struggle in retrieval. They might retrieve the wrong document. Then even if they retrieve the right document, they might retrieve the wrong page, or the wrong place in the document. So there's a lot of interesting things that happen there for different models. And they, all this movement of bringing these large foundation models into document understanding creates a number of other interesting questions, right? So I will not go into detail, but let me spend some time on things that we have done in parallel, not in ELLIOT, but in ELSA, which is the European Network of Safe and Secure AI. And we looked into a number of things there, and of course, I'm very happy that I had a chance to collaborate with amazing people on safety and security, because I don't claim I'm an expert in this kind of things. But we managed to bring all this to documents and to reading systems and to understanding this kind of written information. And we looked into a number of different things. The first one was privacy, right? And if you think about it, we don't have an image net of documents. And the reason for that is because documents contain private and sensitive information. They are copyrighted, right? So it's very, very difficult to put a big collection of documents together. People nowadays, they have fine PDFs and they crawl the internet. But if you really want to do it right, there are lots of questions to be asked, right? So the fact that documents contain sensitive information raises a question, which is, if I train a big system and a model with documents that contain my ID number, will this model remember my details? And can I somehow measure it, and can I somehow attack the model and reconstruct this information? And that is quite true. I mean, if you start training with invoices, you have all account numbers and pricing information about different models. And if you repeat the same information many times in the model, eventually you can just ask the question to the trained model without any document. And in many cases, about 10% of the cases, you get the right answer, right? And that's a big problem, right? So we try to estimate basically how big a problem that was, and then try to solve it a bit. And I will not go into all the technical details, but let me say one thing which is interesting, that in the community of privacy, people are, the first level of attack is what we call the membership inference, which basically means, am I able, given a data point, to know, to figure out if this data point has been seen during training or not. And for us, a data point is a complex thing, right? Because it's a combination of a document, a question, and an answer. That's a data point, right? So the classic membership inference thing would basically look for whether this kind of data point has been seen in training. But in reality, what we are more interested in is whether a specific document has been seen in training. And the idea there is that the same document, the same data point, might have been seen multiple times with different questions, which makes the whole definition very different, right? And we struggled a bit with that. And I will skip because we're already too late with all the details, but we came up with ways saying to estimate whether or not specific data points, specific documents have been seen during training. If you see the numbers there, that's good news for us and bad news for society, because it means basically that we are able to tell that the documents have been seen during training in this kind of models. These are smaller models. These are models of 300, 500 million parameters, right? So it's not huge foundation models. It's very difficult to do privacy research on documents that we don't control, right? But I think it's telling of the problem that we might have. A different thing altogether is robustness, right? Is what happens with these models when you take them outside their comfort zone. And robustness for us is you have questions, you ask questions in a document, you get answers, but then you can create adversarial examples. You can just add a little bit of noise in the document and make these models say the wrong thing, right? And that's a very easy thing to do, right? It might be a small patch of noise somewhere in the document, a small stamp somewhere, or you might just scatter noise around the document and try to attack a specific question. So every time that, the big model asks how much should I pay Demos, I can change this, and instead of 1,000, I can put 10,000, without really doing what we classically refer to as a forgery, right? So a classic notion of a forgery is that you go there and you actually change the content. Here, really, you just add pixels at random places, and you can create this kind of adversarial noise that can trick models. And we're working also on different ways of doing that. And this is basically showing that we can make the model say the wrong thing for a specific question without other questions being affected, right? Without creating collateral damage. And we can do that for one. Depends on the model for a couple of questions. For the models, we can only attack one, right? But it's interesting. We have started basically over the past years. And now we're working also in a different kind of attack where hopefully we'll be able to create a stamp. Every time we put a stamp in the document, then people would not be able to ask specific questions on it, right? We'll see. And the last but not least is explainability, right? So we rely every time more on documents, on models that you ask questions and you get answers, but we need to have some kind of certainty, some kind of confidence that what these models say actually reflect the reality. So where did the model look at to tell me the answer? The answer might be correct, right? But did it just hallucinate it, or it actually looked somewhere in the document? And if yes, where exactly? So the first thing in explainability is ground, is figuring out which are the areas in the document or documents that the model looked at. And hopefully we should be able to get something like this. Say, yeah, the answer is whatever, and this is the places that I looked for the answer, right? And these places should include more than the answer, because we need context to understand that this number is actually the thing that we need. But it cannot be the whole page, right? So we played a bit on this idea, on the idea that you need some kind of grounding which is sufficient, contains all the information necessary, and at the same time is the minimal possible, right? You don't want the whole page, right? And we created a very nice, interesting laws based on mutual information there. But the idea, if you at the high level, is basically that you take a question in a document, you ask a model about an answer, and you also ask the model to create a mask, right? And of course, in the beginning, the mask will be random, right? But eventually, the whole point there is to try to fix it to something that makes sense. And the way we have to fix it is by taking this mask, masking the information in the document, and then just giving only the information that the document told us to the same pipeline and see if they respond the same thing. So do you respond the same if I just mask all the rest and I just use whatever you told me? If not, then probably the mask will be returned is wrong, right? So that's a self-supervised way, without having any annotations, of course, about where the evidence should be, to make the model focus on where the evidence should be, right? And we get good results that are also more than good results. They are also good for humans, right? So it's the kind of thing that humans like more. These are a couple of interesting results in infographics. Infographics are very, very, very strange because they have an aspect ratio, which is very, very interesting to work with. Yeah, and we basically get good focus on the flexibility. So I try to keep it short. I don't know how I'm doing time-wise. Hopefully I managed. But let me just summarize by saying that interpreting written communication is not trivial, right? So people think that, I'll take the latest foundation model and, problem is solved. That's not necessarily the case. There is many visual languages employed or invented as we go, right? So covering them all and coming up with ways to teach models how to deal with whatever written information is there is not trivial. In many cases, you need domain knowledge. I need to know about music to understand what a musical document is, right? So how do you bring this in a reasonable way? We know that reading is an emergent behavior. Even if you don't teach models how to read, they will eventually learn how to do it because it's important, because they're supposed to be working with human-created information, right? So it's interesting to also understand how this emerges during the training process, and that's one of the things that we would really like to look in the ELLIOT project. And of course, the bigger the models become, the less control, in a sense, you can have over them, right? So all these trustworthiness issues start becoming really, really tough. Right, so I think we have a lot of work to do. Thanks a lot for listening, and more than happy to answer any questions.
To do well. 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 To do well.
Of course, everything is really very interesting and enjoyable. But the last part, when you look for the explainability of that one, I like a lot before, please. That one. Of course, depending on the data set you have to train. So that is, I know very well. But have you experienced, or do you know if there are experiences in understanding where the people look at the document, looking at all the gaze analysis and the path scan?
We are working on collecting a data set with eye tracking on this kind of thing. We haven't advanced a lot on this. The last time I did eye tracking was 15 years ago, so now we went back to it because of the explainability thing. But I'm not aware of a lot of work having been done on this, at least not on documents and not in the last 5 years. Right? There was some work on captioning back in the time. There was this conceptual caption that people were not doing eye tracking, they were just moving the mouse around. But I think that there is a lot of interesting things to be done on pseudo interpretation. It's the right time to go back to interaction.
So, thanks.
To do well. To do well. To do well.
So for you, the definition is something static, right? So for a document, you're looking at static documents. Have you considered using some kind of the dynamic information? Let's say you could be some text to associate it to some kind of, I don't know, a music clip or something else in which you have to look into the temporal domain or in video and so on.
To do well.
Yes. For me, a document is a very, very open-ended definition, right? Because it's a substrate to communicate information in writing, right? And this information can be graphical, can be textual, can be in multiple languages, can be a combination. As long as it's a hidden message, that humans designed for other humans to interpret, for me, it's written communication. And we should be making computers participants in this communication. Otherwise, we will not be able ever to use them in urban scenario.
To do well. To do well.
So it's a very open definition, yes. Dynamics in terms of, what do you mean dynamics? In terms of time, the way that text changes over time. We have done tracking of text a lot. In real scenes, yes, we have looked into videos.
When the text is static, text.
To do well.
Right. You have a
To do well.
We have looked into text about images, right? Captions and descriptions. And
to to do well, to do well, to do well.
And we have also looked into the way that we can enhance it by understanding also information inside the images. I don't understand the dynamics that you're referring to. I don't think I get the question right. What is the dynamic there?
To do well.
It's about something that's changed. Then you have some
Right. We have worked a bit on, well, we have worked a lot actually on the way that the visual information, the textual information interact.
Do
And
well.
there is actually a very interesting concept there. Actually, your paper of yesterday was looking into that, right? We know for many years now that all the OCR systems are very dependent on interacting with the visual information, right? So you can very easily trick them the same way like you can trick clip by putting a text on it. You can go the other way around. If you change the visual context around the text, you can actually make the OCR fail. And OCRs tend to rely a lot on their language model, right? So if you try to apply OCRs on things which are out of dictionary, then you have a pretty disastrous effect as well. So if you think about the dynamics between the visual signal and the understanding of the text, for sure, that's something we have looked a lot. And it's a very, very interesting thing. And then I showed also your work of yesterday.
To do well, 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 to do well.
I have a small curiosity also, like basically raised by Nico's question. Would you consider, let's say, the video of a presentation, like the slides of a presentation going on and text changes and interacts with the visual elements, would you consider that a document?
A librarian would consider it a document. I think that there is a document in there somewhere, right? So I wouldn't bother too much with giving a very, very specific definition about what document is, because we have been fighting with that for the last 30 years and we still don't have it, right? So there is for sure some kind of documented information there. And for sure, to understand the whole thing, you need to somehow integrate. Now, whether you want to consider the whole thing as the one document or you want to consider documents appearing in there, up to you. I don't really think it's going to change a lot. No, the fact that we actually have written information there that we need to take into account.
Yeah, but I mean, it's text
To do well.
moving things
Exactly.
a continuous.
Yes. And it's important to take this continuity into account as we interpret. So the fact that this document is changing doesn't make it less of a document, right? And you have to somehow incorporate it into the way you describe this video, right? What I say is backed by the words that are behind, right? So I need to have a temporal interpretation there as well. So yes, by all means, in this way, everything is dynamic. I guess that's all. Thank you very much again for your time.